Hello everyone. In this video I'll be showing some tips and tricks during the reversing of Formbook malware. Formbook is a well-known data stealer, and in this part of the video I'll be focusing on loader stage, which is responsible for unpacking, decoding, decrypting, and injecting the real Formbook code. If you want to get some information about Formbook malware family, you can get it on Malpedia. There's quite a plenty. If you want to download this sample, you can get it on Malware Bazaar. Both of these links to Malware Bazaar and Malpedia are included below my video. I want to tell you something about tools I'll be using. All of these links to tools are included below my video, and I'll be using EXInfo, DTKDZ, XNTSV, DNSpy, D4dot, .NET Babel Deobfuscator, X64DBG, and Labels. X64DBG and Labels I'll be using in the last part of this video. It's something like introduction to part 2. Yeah, so I will show you later. Before I jump to VM, I want to show you one quite a good feature of Malpedia. You can go to Analytics and Scan File, and basically you can scan your file with Malpedia's Yara signature. There are quite a plenty, and in my experience, Malpedia has one of the best Yara signatures because they are covering quite a wide range of malware families. So you can drag the original loader of Formbook, drop it to Malpedia. It will be scanning with the Yara signatures, and what you can see here, it's there's no real match, and that's because the loader is containing many stages, and every stage is encrypted and encoded, and also the loader is written and the stages are written in .NET, and in my experience there are not many good Yara signatures for .NET assemblies. It's quite strange because Yara has built-in support, built-in module for .NET that you can write the Yara signatures for .NET metadata, but as you can see, no true match. But later, in last part of the video, after we reveal the real code of Formbook and we drag and drop it here again, you will see that it's possible to simply match it as a Formbook malware. Now we can jump to our VM. Now we can use EXInfo, and we can check the loader, the original sample of Formbook malware. The original sample is SOA-EXE, and if you drop it to EXInfo, it tells you that it's a 32-bit .NET assembly, and it's a exe file, not a DLL. The difference between DLL and exe file in .NET assemblies is that the main difference is that the exe files has usually the start entry point method, and they are running in their own process space. Well, so we can now use my favorite tool, DNSpy. And now drop the original sample the unspy to check what's going on there. Go to the main. As I said before, it's an exe file, .assembly, so there is a main entry function. This is our interest here, run a new form. Here you can see quite plenty of rubbish. We have to check the initialize component, and in initialize component there are quite a plenty of buttons and labels and other stuff, but the most interesting part is here, the method name. This is basically setting, and the setting is defined here in the method name, and you can see here that here is some creation of a tokenizer object, and the tokenizer object is containing string OOAID and WXMGR and the Champagne 2019 generator. Basically, Champagne 2019 generator is our name of assembly, the namespace, and OOAID is name of resource, and it's quite interesting because you can see it here. OOAID is a resource. Basically, it's a bitmap which will be used in some decoding and converting. Basically, some pixels of this bitmap will be converted to bytes and decrypted, and it will create another module which will be dynamically loaded into memory and invoking some function. We will see it later. So here is the object tokenizer. There is some another rubbish because as you can see, here is some integer value. This integer value is of course larger than this one, so this flag is true. Not true is not, so this will not be executed, and this is true. Not true is not, flag 4 is not is true, this will be executed, flag 5 is true, this will be executed, and this is nothing. So basically this all is doing nothing. And here is the most interesting part, because you can see here that we can start here. You can see that iteration count is some decrypting method, and to iteration count the arguments are IG class and method Unity3D. Unity3D is a method which gets resource which has name Unity3D, and Unity3D you can see here, Unity3D, and in Hex you can see that it's looking like some executable already, some kind of encoded form. So jump back, and it as you can see, it's getting the resource and returning the bytes. The bytes goes to the iteration count. Here is some decoding routine, and you can see here another resource in IG class, method name, method x, and x is getting another resource which has name x, and x is some string. So I think that this string will be used for decrypting, maybe for some XOR cipher. And you can see it here, the x goes here, the bytes, and you can see here in XOR routine. Yep, and returning some data. And as you can see, this data will be loaded to the memory, and the object which is loaded to the memory is passed here to synchronization context. So Unity 3D as a resource will be decoded to the module. This module will be dynamically loaded into the memory, and then the object in memory is passed here to the synchronization context, and also the tokenizer, as I mentioned before. So if you put a breakpoint or set a breakpoint here, you will get you can see the loaded module. Wait, I can put a breakpoint here and put a breakpoint here. Here, the decoded module, the Unity 3D, will not be in memory, but here on this breakpoint it will be already loaded in memory, and you can see it. You will see it in a modules window, and we can dump it from memory and check it later. So let's start debugging. Okay. Yep, and now we are on the first breakpoint, and you can see the modules window. The modules window will show you only the SO8. It's the original sample and nothing more. But if you continue, here is our another module already loaded in memory. We can right click on mouse and save module from the memory and save it here. Now, if you want to check that, you can see what's going on next. It's this is the object of the loaded module, and you can see that it's getting type of a beautiful UI, beautiful button, and it's reference here, and it's getting method in a beautiful text box. And this method, you can see it's dynamically invoked from here, and argument to this method is null and the tokenizer object you saw before, which is working with the OOAID resource. So we can now load the module, which is already loaded in the memory, to the NSPI. You can double click on it and it will show you here. You can set a breakpoint here now, and if you try to find the method as you saw before, the beautiful text box, which will be dynamically invoked, you can see it, but you can see also that it's you can see it here, you can see it now also here, that it's obfuscated, and I really don't like obfuscated code. So now I want to show you how we can manage to deobfuscate this second module and patch the original sample, original loader, to load our deobfuscated code, deobfuscated module. So basically we replace the resource and patch some code in the original sample. So we can put a breakpoint in already deobfuscated code. So let's stop debugging. Can file and close all. And now we can jump back to the to our dumped module. We can call it, we can leave it as it is, and again we can use exe info. What it is, if it's a .NET assembly, probably yes, and if there is some protector, exe info is quite very good with detecting the .NET protectors, so obfuscation methods and others. If you drag and drop it here, you can see again that it's a DLL .NET assembly. So there's no entry method, and you can see that it's created in .NET Reactor. So basically, it means that probably the .NET Reactor obfuscation is used here. You can check it also in Detect It Easy. which is quite very good with detecting some obfuscators and others too. So again, drag and drop it here, and it will show you that the protector is .NET Reactor. A library is written in .NET. Yeah, so basically what we already know. Thank you, that is easy. And now we can use d4.dot, because I already know that d4.dot is supporting .NET Reactor, so it will easily deobfuscate the code. So drag and drop it to d4.dot. Detected .NET Reactor, cleaning, renaming, saving. Okay. And here we got the clean version. Now we can delete this one. Yes. We can rename this as a stage 1 Unity 3D, because it was a Unity 3D resource. Yes. Now you can drag and drop it here to check if to check if it's already deobfuscated, and you can immediately see that the code, yeah, here is nothing and nothing, no, not rubbish, and the beautiful text box, yep, that's better, far better, already obfuscated. And now we have to replace this for the resource in the original sample, and patch some code in the original sample which is working with the resource, the decoding code, because we will not be using that, because this is already decoded, deobfuscated. So yeah, I will show you. So let's close all, find the original sample, load it here. Now go to the resource, find the Unity 3D and check the type of this resource, and you can see that it's a type of byte array. So just delete it, and now you create new resource. Name will be, oh, I have to copy the name. Now create the new resource. Type is byte array. Name is Unity 3D, and load here our decoded and deobfuscated Unity 3D. Open. Okay, and it's here. Now it's time to patch the code, which is working with the Unity 3D resource, because we don't want to decode it again. So go to the main. Again, form1, initialize component, and here is the name, setting, and here is the function. Yeah, this function is working with the Unity 3D, and you can see that this function is only getting the Unity 3D and returning as bytes, so it's okay, we can leave it. And iteration count is performing the decoding and returning the decoded bytes. We don't need this because our Unity 3D, as we patch it, is already decoded and deobfuscated. So just simply press mouse right click and press edit method C#, and basically you can edit the C# code in the decompile view. You don't have to use the edit EIL instruction. I will show you later. And mark it and delete it. Basically it will only pass data 1, which are the bytes of the resource Unity 3D, and it will return them. So that's okay, that's what we need. Compile, and if you find again the iteration count, you can see that it's only returning the data. So that's okay. But there is one thing: if you find some sample which should be where the edit method C# doesn't work, you can edit the IL instruction, and in my experience this works every time. Yeah, so you can edit the IL instruction, but you have to have some more experience with the C# and with the .NET coding and reversing. Well, now we have our patched original sample, so just save it, file, save module, and save it as SOA patched. Okay, again, file, close all, and find the patched one sample. Yes, it's here. And you can see that in the resource we already have the Unity 3D, and if you check the in Hex editor, you can see that it's the mzip, is the exe.net assembly. Oh, sorry, it's a DLL, but it's already decoded and the code is also patched, so everything should work. Okay, so again, go to main. In main, the form1, initialize component, and scroll a little down. Here is the setting name, synchronization context. Here is the point that the module will be already loaded in memory. So put a breakpoint here, start debugging. Yep, we've reached our breakpoint, and you can see that the beautiful text box will be dynamically invoked here. So now you can go to the modules window, and if you don't have this window here, so just go to the debug windows, and here is the modules windows, and it will show it here. Beautiful. And if you double click on it, you are there, and go to the beautiful UI, beautiful button, and beautiful text box, and put a breakpoint here. As you can see, the code is already obfuscated and loaded in memory. Just continue, and you reach the breakpoint in the deobfuscated code of our next stage module. Okay, there is only some sleep, so continue. And we have to investigate this method. Method 1 has a span draw, and here is the loading. So there is another loading, so another stage will be loaded to the memory, and you can see that in this decoded assembly there will be calling entry point. So I think that it will be the exe.net assembly, not a DLL, because it has the entry point. And it's getting the type, object here, object reference, proc name is invoke, and you can see that this object of entry point is called by name, invoke, entry point, call type get yes, and arguments are null. So basically, what does it mean? If we manage to dump this next stage module, .NET assembly, the exe file already decoded, we can deobfuscate it, and we can manually run it and debug it in the dnSpy. We don't need this anymore, the previous stages, because there is no arguments, but we can specify the arguments, but it's running in its own process, so there's no problem. So check what happens here. Yep, we can see that the resource name argument is OOAID, param is WXMGR, project name is Champion 2019 generator, so the namespace, and here is the method 0, And method 0 is getting the resource called OOAID and returning as a bitmap, because we saw already that the resource is you can see it here, it's a bitmap. Yeah, so it's getting the resource here and returning the bitmap. Bitmap is here, and it goes to the method hazard, which is returning the byte array. Hazard is performing some, yeah, it's getting the pixels, and all the pixels are some kind transfer to byte array. Yep, we don't need to bother with this. Some kind of decoded pixels to byte array goes here, and these bytes goes here with the second argument as a parameter, and it's a wxmgr, so I think there it will be some decoding maybe. Yeah, you can see it here that it's XORing and decrypting and other stuff and returning the byte array. So here is the first decoding, and what's going on here? Method draw, yeah, it's performing the Gzip decryption. So these bytes which goes to this method are already compressed with the Gzip, and here is the decompression, and it's returning the raw assembly, and the raw assembly is loaded. So if we put a breakpoint here, here and here, we can here the another module will be already loaded in memory and decoded and obfuscated. We can check it and continue, and you can see that here is another module. Let's save it, save module, and save it here. Okay, before we jump to the next module we already dumped, we can check what's going on next. Basically, it's invoking the entry point and go to exit. So we don't need this anymore. So let's stop the debugging. You can again file and close all. And go to the yeah, this is the stage 2 module, and if you check it in again exe info, you will see that it's it can detect that this is also obfuscated. It's a 32-bit .NET assembly. It's a exe file, and you can see that probably Babel obfuscator was used. Babel obfuscator is a commercial obfuscation tool for .NET code. So we just need to use some deobfuscator for Babel. I would like to use the d4.dot again, but according to my experience, d4.dot didn't produce a result I expected. So I tried another open source deobfuscator for Babel, and the deobfuscator is available on GitHub. You can see it here. The link to this Babel deobfuscator is also included below my video. And you have to compile it, but I did it and it was quite smooth, so there is no problem with that. So let's jump back. And before we start to deobfuscate, I would like to show you the obfuscation form. You can see it here. Go to main, and the main is here. Yeah, you can see here that method class name and method names are Unicode encoded, and there are quite many for loops and also many switch cases, and all is obfuscated. So now we can use the .NET Babel deobfuscator. Let's copy that .NET Babel obfuscator 32-bit because we have 32-bit sample. Run the Babel obfuscator. It wants a name to unpack. And it will perform the unpacking. After it unpacks this sample or deobfuscated the Babel obfuscator, you will see that it's not ready for the analysis yet, and I will show you in the NSpy. Yep, it's complete. We can check that. You can delete this original and only copy this clean one here. And if you check that in the NSpy, what you got here is basically, I will show you that this was the sample before. Yeah, many for loops and Unicode encoding and switch cases and others. And this is the sample after the Babel deobfuscation. And you can see that there are no for loops, there are no switch cases, but still the Unicode encoding of classes and methods remains. But with this kind of encoding, we can or obfuscation, we can deal with default easily because it can handle it very well. So file, close all, and now it's time for d4 dot to shine. d4 dot, let's get the clean one version, and yeah, detect unknown obfuscator, but it will clean the Unicode encoded method names and others. Yep, we are ready, and we can delete this one, and this we can rename as a stage 2 AID, and drag and drop it to the NSpy to check that what is going on. Yep, go to the main. You can see immediately that it's already deobfuscated, and yeah, basically this is the last stage of the loader, and it's performing many actions, so I want to cover all. So let's go. So here you can see that it's getting the location of the assembly, and here are some checks, and I want to explain something that these checks are according to some, you can see here, some config string, and basically what it means that you can config this loader if you compile it, and you can config this loader to use for example anti-VM checks or another URL for downloading another sample and executing. You can config it for whatever, and according to the config string, it's performing this action: method 1, method 0, method 2, method 1 again, but in class 0, and others. So let's check the methods. What is going on here? Method 1 is simply checking mutex. Yeah, it's trying to open mutex, and if it's able to open the mutex, the application ends. So basically, it means that it's checking the another instance of this process. Yep, so we don't need this, we are not interested in this. Here is sleep, nothing interesting. Method 0 here, some message box maybe showing something. Here is method 2, and yep, so what is method 2? Method 2 is checking the VM environment. It can check the VirtualBox, it can check the wine, it can check the VMware tools, VMware environment, it can check the QEMU. Yeah, so we are not interested in this too. We will patch all of these methods and delete them later. And method 1, again, string builder. The string builder is username. So username here it's checking SBIDLL, which is a part of Sandboxy. So if it's running in Sandboxy, it goes to exit. If the username is user or sandbox or virus or malware or Schmidity or current user, it goes to exit. And what is here? String 0. String 0 is an initial argument, so it's a location of the assembly. So if the location of the assembly is containing the a virus or sandbox or sample or file exe, it goes to exit. We are not interested in that too. Method 5 is what? Method 5 is downloading another file from provided URL. I already checked this sample and I know that the config string is not containing any URL and it's not configured to download another sample. So we are not interested in this method too. And here is another method, another check. You can see method 4. And method 4 is performing method 4 is performing persistence via scheduled task. So we are not interested in that too. And what's next? Method 8. Method 8 is we can leave method 8 and method 9. So basically we can delete all of these what was before. Now again edit method C# and you can delete all of this to method 8. Yep, and compile. Again to the main, and you can see here that all other stuffs were deleted. Now it's time to save it. Save this patched version. File, save module, and save it as patched. Okay. Again, file, close all, and load here the patched version. And go to the main and put a breakpoint here. Start debugging. Okay. Yep, we reach our breakpoint, and now it's time to step over and this method was not performed. So only method 9 will be executed, so we can check the method 9 before execution. Method 9, and method 9 is it's getting its initial argument is some integer from the config file, config string, and you can see the method 10, and here is some method byte 0 byte. It's byte 0 is set by these methods, and you can see here that it's so the arguments for the method 6 is method 10, which is doing something, and bytes which are set here. And you can see that method 0 is working with this string and with some string here. And what is going on in method 0? Method 0 is getting the resource again resource and returning bytes array, and we can see that the resource is a name GHYTXXW. So the resources, and you can see it here, GHI. Yeah, it's about 186, almost 186 kilobytes. So it should be the real Formbook code. So it's getting here the resource and returning the bytes. This string is probably some decryption key maybe, and it all goes to method 2. Method 2, yes, as I already told you, that these bytes are the bytes of this resource, the real Formbook code. The string is used as a, you can see it here, bytes, and for decryption routines. And after this decryption of the resource GHYTXXW, it goes to the method 1. And here you can see another decryption. And that's all. So basically, what does it all mean? It means that this decodes and decrypts the original Formbook code. And what is doing this method? Yeah, you can see it here. We put a breakpoint here. So here there will be the resource GHYTXXW already decrypted, and this parameter is true, and this method is performing something else, and it all goes to method 6. So we can put a breakpoint to method 6 and go back. We have breakpoint also here, so continue debugging, and we are here. Here are some switch cases, and the initial argument is some integer from the config string, and we can see that our sample is configured to use our assembly location. And what does it all mean? It means that according to the configuration string, this executable or our assembly sample could be used for the process hollowing injection method. So according to our config, our sample will be again spawned in suspended mode, and it will be performed the process hollowing injection to our sample process, and this will be not used. So continue again, and we are on the method 6. Here is the method 7. We can jump to the method 7, and method 7 is the most interesting part and the last part. So let's continue and check the locals. You can see here that the string 9, you can see here string 10 is some string containing path, is used for as an argument in the create process. So basically, what does it mean? Create process. String 9 is a executable path which will be used for the process creation. It's our sample. This sample will have command line arguments containing path, and this one is quite interesting because 1, 2, 3, 4, 5, 6. It's a sixth argument of a create process API call. And if you check the Microsoft documentation, create process function 1, 2, 3, 4, 5, 6. 6 is a creation flags. And if you check the creation flags, process creation flags, and what you can see is that 4 in hexadecimal or in decimal, it's okay. It means create suspended. So if you so here is 4. This is 6 argument. So basically, it will create a process of our sample, the stage 2, and it will be created in suspended state, and the command argument will be path. Okay. So let's check it here. Let's put a breakpoint here. What's going on here next? We can see get thread context, read process memory, unmap view of section. It's typical for process following. Virtual alloc X. This is API call for allocating memory in specified process, not in our own process. We can use virtual alloc for our own process, but virtual alloc X is there is possible to allocate memory in other processes. Write process 1, write process 2, and write process 3. Now after that we can see the set thread context. Yeah, we can see above 64 set thread context. It's used only when you are in 64-bit process and you are trying to set context in a 32-bit process. You are using above 64 set thread context API call, but we are in 32-bit and we are setting the 32-bit, so it should use the set thread context. Resume thread. Yeah, we have already all breakpoints set, and now we can continue to reach our next breakpoint. Now we are here, so there should be a new process already created in suspended state. We can check it in a process hacker or process explorer tool. We can see here this is our original sample. No, original sample. This is our stage 2 sample, and this is our new spawned process in suspended state, suspended mode, and you can see the command line is containing path. Well, what we got next? Next is virtual alloc. So continue virtual alloc and check the vocals. You can check that arguments to virtual alloc are process handle. So basically, it's a handle to process this suspended process, and other is base address where the memory will be allocated. So num3 and num3 is 0040000, so typical base address for 32-bit applications. And this is size. Size is int yeah, 2E000. Yep. And this is what? This is allocation type, maybe. Yeah, you can see the base 16 that it's a 3000. And if you check the virtual alloc X in Microsoft documentation, the arguments which was 1, 2, 3, fourth argument. 1, 2, 3, 4. Yeah, it's allocation type, and allocation type, if you scroll a little down, allocation type, if it's equal to 3000, it's a mem reserve and mem commit. So allocation type is mem commit and mem reserve. Go back, and what is this? It's 40 in base 16. So in hexadecimal it's 40, and if you check the last argument to the virtual alloc X, it's a protect. And if you check the protect, you can see it here, and the protection is if it's equal to 40 in hexadecimal, it's a page execute read write. So what does it mean? It will allocate memory in on base address 0040000 and the size 2E000, and memory segment will be flagged as a read write execute. So let's check the memory in a process hacker. Memory, you cannot see here something on 40000 address, but if you check it after execution, continue, and if you check the process hacker again and press refresh, you can see on address 40000 it's 184 kilobytes. segment, and its protection is read write execute. It's empty now, but we can check it later. Jump back to the unspy. We have here our first write process memory, and the first write process memory, this is the first argument is process handle. It's our process in suspended state. num6 is base address of the allocated memory, and byte1 is a variable is our decoded bytes of Formbook malware, and int integer 2 is a variable size, so 512 bytes. So let's continue. You reach the second write process memory, and if you check again the memory map, memory in this segment, reread, and you can see that it's already written here. First 500 bytes, yeah, to here. Okay, we can continue, and we check. Here is the second write process memory, and you can see process handle. Base address is num6 is again base address of allocated memory for 00000, and num9 is num9 is 1000 in hexadecimal. What will be written here is array, and array is some kind of calculated blocks from the byte1 decoded Formbook, and you can see that the array length is the fourth argument. So if you check, if you continue, go to the memory and scroll a little down to address 1000. Yep, it's here. And now press read, and it's already populated. Okay, you can see that it's quite plenty of bytes. So basically this is all code of a real malware Formbook, injected in new spawn process in suspended mode via process following method. You can close it, and what is this process memory, write process memory? It's the third one, and you can see that process handle is the same. You can see that the base address is quite strange, num4. Num4 is here. You can see 7EFDE000. It's absolutely not a part of the allocated memory. And if you check it in process hacker, 7EFDE, 7EFDE, it's a process environment block structure, 32-bit structure of process environment block, and it writes there 4 bytes. The size is 4, and bytes are here. Bytes variable is here, and you can see it's it's a 004000 because it's a little endian order. So it's basically the base address of the new allocated memory in spawn process, and it's written in process environment block, and on address in process environment block PEB +8. So basically we can check where it goes. So minimize it and run this tool, which is called XNTSV. And for what is used this tool, what is the purpose of this tool, you can check it on GitHub. The link to download this tool is also available below this video. XNTSV program for detailed viewing of system structure. Basically, this is what we need, and it could be really helpful if you don't want to use Windows debugger or don't want to read header files or some another documentation or something like that. But it's quite easy of use, so you will see now. Just attached to the process, the suspended process, you can see in process hacker that it's process ID is 2236. 2236, so 2236. Here, press start, and here is the process object, and you can see that you are immediately in the process environment block structure, and on the address process environment block +8 is image-based address. You can see now that image-based address is E80000, but after this execution it should be rewritten to 40000. So press continue, you reach the set thread context. So this should be already written. Go to xmtsv and press reload and check this image-based address. Yep, it's a 40000. And why this loader is performing this is because you can imagine that in part 2 I will be more focusing on reversing and analyzing the real Formbook code, but usually the Formbook code is some kind of shellcode blocks. Yeah, there is no import segments, there is no sections, there is only section txt, like text section of code. Yeah, so it's basically some blocks of shellcode, and shellcode is usually performing searching and loading and calling API calls via searching the process environment block structure and loading, finding some modules there, the base address of these modules, and searching the APIs which this module have, and which this module has, and calling this module via this routine. Yeah, so that's why this process environment block has to be patched to point to the address 004000. Yeah, we are in the set thread context. Basically, set thread context, what does it mean? It's setting the registry of the thread, execution thread, and registry state. And basically what does it do? It's setting the EAX register to point to our entry routine for new created thread. If you press continue, we are on the resume thread, and if you press resume here continue, the suspended thread will be resumed and the execution start. But we don't want it. Now we can close this, close process hacker or minimize. We can close it. And now it's time for the last part, which basically some like showing something which will be part of the second video, the reversing of real Formbook code. And start the x64 DBG, we will be using the x32 DBG, the 32-bit variant, because we will be debugging the 32-bit sample. 32-bit and start. Now we attach this debugger to the suspended process where was performed the process following the injection of the real malware, real Formbook code. File, attach, and we can attach to the suspended one. It's the one with the command line arguments path. Just attach to it, and you are on the user thread start in NTDLL. And you can see here that the EAX register, because of set thread context call, is set already to the entry routine of a thread. So just press right click and follow in disassembler and to put a breakpoint there. Now you can here press continue, because this is basically catching only some errors. So, and this method is starting new thread, but it's not configured according to the configuration string. It's not performed. You can see it because I can press step over and step in, and you are in the return. You can see, yeah. So it goes to the exit. So basically, you can close the dnspy, and you are in the 64 dbg. And if you press now the continue, you are on the entry point of the real Formbook code we reveal with all these stages I cover in this video. Now is the time for the labels. I will be more focusing on the labels and IDA and reversing the real Formbook code in the next video, but a little introduction for this, how labels and IDA could be really useful. Just go to the IDA, start IDA instance, press go work on your own. And now you can see that in the labels tab, you have the option load stub database, which basically creates a new empty database. You can save it on some at some writable location. Save it here, and yeah, press the portable executable. Basically, it creates an empty database, and it creates something like an empty exe file. You can see it now after a while. Yep, there is some problem. Okay, it's no problem. We can delete this, start again, and yeah, it's quite a good recovery option. Okay, sample, load existing, repair. Yep, when we are here, you can see that it's an empty database. And what we have to do now is basically in our VM x64dbg, there is plugin basically labels debugger backend. You can see in the logs, if you check the logs, that this labels plugin is bounded to port 3852, and it's already listening. You can basically click on labels and settings, and you can see here the IP address and the port, test connection, and connection is successfully connected. Okay, so now it's time to perform IDA dump, wipe all and import. It basically delete all this database which is already empty, but it deletes it, and import a segment or segments of memory from the debug backend. From this, you can see it here in memory map, and what you want to be exported to the IDA. So we choose the address 0040000 here, read write execute, and yep, we can select it, press OK, and it's exported from the x64 dbg. We can press overwrite to overwrite this database. We don't want to backup it. and it exports the memory segment from the debug backend to IDA. And after it, I will show you some quite useful tip. It's almost done. Yeah, it's still running. Yep, it's done. So check the exports, because we are on the entry point. The export should be here, treated as an entry point. You are here. Yeah, you have to press undefined, and again to the exports. You are on the address of the entry point of real Formbook code, and here is the main function. Basically, here you can see that the 420 function was recognized, but now it's quite useful to use Lumina and pull all metadata, and you can see that many of the functions were already reversed from somebody, and you can use this all metadata, the labels, names. You can see that this function is already named as main. You can jump to the main. You can see the initial memory, control block, and adjust token. Also, there will be performing some adjust privilege, and you can see call exit and other stuffs. But what is really useful, that you can send these all labels and function names to the IDA backend, IDA debugger backend, the debugger backend of the labels, and you can see that here are no names for the functions. But after we press a synchronization, sync labels now, and it's done, check that again, and you can see it here, main. If you go to the main, follow in disassembler, yeah, you can see that here is some initiating memory, and control block and adjust token. If you want to follow in disassembler, yep, adjust token, and you can see adjust token privilege and other stuffs. Basically, you imported all of the labels and function names to the debugger backend for the labels. It's quite very useful, but I will be more speaking about this and about the reversing of the real Formbook code in next part of video. So now you can do the last. What I want to show you is that you can now go to the, for example, Hex View. You have here basically all the memory segment, as I mentioned you, and you can dump all this from the IDA. If you go to the edit and go select all, and you can now basically go to the file and no, export data, and press as raw bytes and save it as for example, save it here and save it as Formbook code decrypted.bin. Press OK, save, and export. Now jump to the, it's here, Formbook code decrypted export decrypted bin. You can see it in no, you can see it in one. Okay, you can see it's all the memory, some MZ header, executable, nothing interesting. You can check also the with pbur that there is no section other than text, and then there are no imports. You can check the section there is only the text section, so the code, and there is no import table, there is no imports. Yeah, so that's why the loader was performing the process environment block patch. Yeah, because this code in the Formbook code will be working with the process environment block a lot to load and to find some API calls which will be dynamically called during the runtime. And now you can go back to the malware, just drag and drop the Formbook code which is decrypted, and you can see matched true Formbook and Formbook. So yeah, that's Formbook. And that's all in this part of video. I hope you enjoyed it, and see you in the part 2, where I will be focusing more on the real Formbook code. Thank you for watching.